There are many settings in which we can ask questions related to some type of a stability principle. Here's one involving a competition between two enterprises. Suppose we have two television networks, whom we'll call A and B. They are in primetime programming slots, and each network has n TV shows. Each network wants to devise a schedule, an assignment of each show to a distinct slot, so as to attract as much market share as possible. Here is the way we determine how well the two networks perform relative to each other given their schedules. Each show has a fixed rating, which is based on the number of people who watched it last year. We'll assume that no two shows have exactly the same rating. A network wins a given time slot if the show that it schedules for the time slot has a larger rating than the show the other network schedules for that time slot. The goal of each network is to win as many time slots as possible. Suppose in the opening week of a full season, Network A reviews a Schedule S and Network B reviews a Schedule T. On the basis of this pair of schedules, each network wins certain time slots. According to the rule above, we will say that the pair of schedules ST is stable if neither network can unilaterally change its own schedule and win more time slots. That is, there is no schedule S prime such that network A wins more slots with the pair S prime T than it did with the pair ST, and symmetrically, there's no schedule T prime such that network B wins more slots with the pair ST prime than it did with the pair ST. So the analog of Gale and Shapley's question for this kind of stability is the following. For every set of TV shows and rating, is there always a stable pair of schedules? Resolve this question by doing one of the following two things. So we have two choices. A, give an algorithm that for any set of TV shows and associated ratings produces a stable pair of schedules. Or B, give an example of a set of TV shows and associated ratings for which there is no stable pair of schedules. The answer is
now
B.
Suppose
we provide a very simple
schedule
example.
1, 3 and
Suppose
network B
that
schedule 2, 4. Then network B has
S
some choices
to
win more
1,
if
3,
the
and
network
T
B
equals
switch
to
4,
4.
2. But then after
If the
network B
schedule
switch to
is
4,
for
2,
network A is put
has
1
lost
at the
one
first
wins.
slot and 3
So
at the second slot,
it will
and
have to
if
reverse
the
the
network
schedule
B
2, 3,
put
1 and
2
so on. So two
at
networks
the first slot
they
and 4
will
at the second slot,
doing all the things
then
all the
there
time.
is
So
a
which
choices
means
that B can
there's no
switch
stable pair
2
of
and 4
schedules
so that
for such an example.
the network B will win at least for the second